So let's continue the worksheet. We finished numbers 1, 2. Did we do number 3 last time? Or did we do number 2? Don't remember if we finished number 2 or not. Okay, 1 and 2. Let's do number 3 then. So please read the question. So you're driving a car traveling at constant velocity of 25 meters per second. When you see a child suddenly runs onto the road, it takes 0.45 seconds for you to react and apply the brakes. As a result, the car slows with a steady acceleration of 8.5 meters per second squared and comes to a stop. What is the total distance of the car moves? What is the total distance that the car moves before it stops? So this problem has 2 parts. One is the part that has constant velocity, and the next part with acceleration. Okay, the negative acceleration. Once you apply the brake, we call the acceleration as deceleration or negative acceleration. So let me just write a picture here. So that's the road. Okay, you're driving on the road. So you're moving at 25 meters per second. And it takes about 0.5 seconds to apply the brakes. Okay, so that's your reaction time. So until you apply the brakes, your car is moving at a constant speed. So at this point, you apply brakes, and then it comes to stop after some time. Okay. So this is deceleration part, and this is constant speed part. Okay, so let's first deal with the constant speed part. For constant speed part, when there is constant speed, there is no acceleration. The only one formula we use for constant speed is this formula: V is equal to distance over time. Okay, that's the only formula. And here we are asked to find this distance, delta x. You can say displacement. So when you are traveling on a straight path, basically distance and displacement are same. Okay. If you are on a zigzag path like this, then the total path is distance and the shortest path is displacement. But if it is a straight line, both the distance and displacement are same. So delta x is v times t. Okay, delta x is v, 25 meters per second. Time, how long it takes to apply the brakes. So it says your reaction time is 0.45 seconds. So that gives you 11.25 meters. That's the distance traveled in the first part. Now for the deceleration part, once you apply the brakes, for the deceleration part, we have 3 formulas. We have this formula: A is equal to V final minus V initial over T. We have delta x is equal to V final squared minus V initial squared. You don't need to write all these formulas. I'm just showing you what kind of formulas we have. We need to figure out which one would be the relevant one. So and then we also have delta x is equal to VIT plus 1/2 AT squared. Okay. So now let's look at what information we have. Okay. So we are given the initial speed. Okay. Up to this point, the speed is still the same, okay, 25 meter per second. And once you apply the brakes, now your car will slow down, okay, and then eventually here your car will stop. So that means your initial speed is 25 meters per second, and final speed is 0. And your acceleration. Now, when you are speeding up, your acceleration is positive, and when you are slowing down, your acceleration would be negative. If your question doesn't tell you or doesn't mention the negative sign, then you still need to put the minus sign here. Okay, that negative sign means you are slowing down. Okay, negative means slowing down. So, as a result of applying the brakes. So we have these three quantities, and out of these three quantities, which formula would have those three quantities? So here you see this one has VF, this one has VI, and A. So that means this is the most relevant formula. Okay? This cannot be used because we don't have the time. That means we'll be using this one. So delta x, and that's what we want to find. Delta x is VF squared minus VI squared over 2A. V final is 0 squared. V initial squared, 25 meters per second squared, over 2 times A is negative 8.5 meters per second squared. Okay, and then you will use a calculator to get a final answer. So if you do that calculation, you'll get delta x equals to 37 meters. Now we have this part. Let's call this x1 and this x2, okay, instead of writing same symbol for both. So the total distance traveled before the car comes to halt is delta x is equal to delta x1 plus delta x2. So that means it's 11.25 plus 37. That is equal to, you get 48.25. Now you need to use the sig fig rule. So the lowest sig fig between these two numbers is 2 sig fig. This one has only 2 sig figs. So your final answer should have only 2 sig figs. So you need to round this off to 48 meters. Okay. So that's number 3. Now let's look at number 4. Let's read the question. So you are designing an airport for small planes. One kind of airplane that might use this airfield must reach a speed before takeoff of at least 27.8 meters per second and can accelerate at 2 meters per second squared. If the runway is 150 meters long, can this plane reach the required speed for the takeoff? If not, what minimum length must the runway have? Okay. So this is number 4. So the takeoff length or the runway length is given. So that's x, delta x is 150 meters. So the plane has distance of 150 meters before it takes off. Okay. It can travel maximum of 150 meters, not more than that. And the speed for the takeoff needs to be 27.8. That's the final speed, 27.8 meters per second. Okay. And the plane starts at rest in the beginning. Okay. On the runway, the plane starts at rest. Okay, here. Vi is equal to 0, and then just before takeoff, its final speed would be 27.8 meters per second, and then it takes off. So it will cover the distance of 150 meters before it takes off. Okay. Actually, we need to this is not the final speed. So we need to figure out whether or not with that distance and with the given acceleration, so acceleration is given. So you start the plane from the 0 speed and you accelerate that at 2 meters per second squared. And just before the takeoff, will it reach the speed of 27.8 or not? That's the question, okay? So this is not what we are using. We just want to we want to figure out whether or not we'll be able to reach that speed. So we have these three quantities, and then we'll be finding VF, okay? And we'll compare that VF with this VF. So this is the problem with acceleration, and the problems with acceleration, we can use three formulas. So we need to figure out which formula would be relevant here. So VF minus VI over T is A. Delta X is equal to V final squared minus V initial squared over 2A. And delta X is equal to V initial times T plus 1/2 AT squared. So which one we want to use? Let's see that. So we don't have time given, so this would be not relevant. And then we have distance given, we have acceleration given, we have initial speed given. That's what we need to find. So it seems like this is the relevant one. Okay. Here, this is not relevant because we don't have time. Okay, so we cannot use that. So let's use this one. Okay. So in order to find VF, we want to rearrange this equation in terms of VF. So take this 2A to the left. So we'll have delta X times 2A. That is equal to VF squared minus VI squared. I'm just rearranging the terms using this equation. And then VF squared would be, taking this to the right, to the left, VI squared plus 2A delta X. Okay, just rearranging the terms. And then VF would be equal to square root of VI squared plus 2A delta X. So does this make sense? Like the way sometimes people understand this is by doing this kind of thing. Let me show what you do. Let me use different color. So we want to get rid of 2A here, so multiply both sides by 2A and 2A. So you cancel 2A and 2A, and then you have 2AX delta X is equal to VF squared minus VI squared, and then to get rid of VI on both sides, you add VI squared and VI squared on both sides. Okay, you cancel that, And then now you have Vf squared is equal to that, Vi squared plus 2a, no, we don't have x here, that's times, okay, delta x. So that's what I got. Okay? And then in order to get Vf, you need to remove this square. To remove that square, you need to use square root here. Okay? Now let's plug in the numbers. Vi is 0 initial velocity to the acceleration of the plane is 2 meters per second squared. It's speeding up, so we don't need to use minus sign, unlike in the previous one. And then delta x is how long we want to run the plane. So it will, 150 meters. So do the calculation. You'll get 24.5 meters per second. Okay, and now you compare this with the proposed speed, which is 27.8 meters per second. So that means this is not enough speed. We want to get 27.8, but that doesn't give us 27.5. So that means the acceleration of the plane is not enough to reach that speed. We need higher acceleration. So the second part, we need either higher acceleration or we need to run the longer distance. Okay, there are two ways to achieve that speed. So either you need greater a or run longer distance. And the question is asking what would be the length of the runway to achieve that. So on part 2, we want to find delta x. Okay? We'll be using the same acceleration. It'll take a little bit longer distance to achieve that, greater than 150 meters. So Vi is again 0. Now again, we can use the same formula. So our purpose here is to achieve 27.8 meters per second in the final stage. So delta x is V final squared minus V initial squared over 2a. So V final is 27.8 meters per second squared. V initial is 0. And then 2 times acceleration of the plane is 2 meters per second squared. So that will give us 193 meters. Okay. And the question has a significant figure of, the lowest significant figure in the question is 2. That means we need to round this off. Okay, so round this off to 190 meters. And that's the answer. Okay, so that's number 4. So let's look at number 5. Any question on number 4? So please read the question for the number 5. This one is pretty straightforward. You should be able to figure that out. So how long does it take a car to cross a 30-meter wide intersection after the light turns green? If the car accelerates from rest at a constant 2.0 meters per second squared. So it's asking the time, okay, how long it takes to cross 30 meters distance. So starting from here, it'll be crossing 30 meters, and we need to find the time, okay, delta t or t. And starting from here, it will accelerate at the rate of 2 meters per second squared. Okay. And it starts from that point. That means initially it's at rest. Okay. It starts from zero velocity. So again, we have three formulas for any kind of accelerated motion. So out of those three, you need to decide which one would be relevant. So let me just write it. Vf minus Vi over t, we have that. And we have delta x is equal to Vi squared minus Vf squared minus Vi squared over 2a. Delta x is equal to Vit plus 1/2 At squared. So we are finding t, okay, or delta t, same thing. We are given a. We don't have this one, okay, it's not given. That means this is not useful. There's no final velocity given. This one also has final velocity, but we don't have final velocity, so not useful. This one, this is given, delta x, distance traveled. Initial velocity is known. A is also known, so that means that's useful. So let's use that. So delta x is equal to Vit plus 1/2 At squared. So we want to cross the distance of 30 meters with initial velocity of 0 in time, some time t, which we want to find. Okay, 0 times t plus 1/2. We are accelerating the car at 2.00 meters per second square, and then time is t squared. So we need to solve this to find t. So 30 meters, so we can cancel this one and this one, 2 and 2. So we'll have t squared left on the right side. So that means to find t, we need to take square root on both sides. So when we take square root, that would be square root of 30. And square root of 30 is 5.48 seconds. And our significant figure should be 3 digits. So that's the answer. Okay. So both the numbers in the question have 3 sig figs, so our answer should also have 3 sig figs. Okay. So that's number 5. So last one, let's look at number 6. Please read the question. Suppose you want to design an airbag system that can protect the driver in a head-on collision at a speed of 100 kilometers per hour. Estimate how fast the airbag must inflate to effectively protect the driver. How does the use of a seatbelt help the driver? So we don't need to answer the second part because we will answer that in the next chapter. So we'll only answer the numerical part. So let's see the scenario here. Number 6. So initially the car is traveling at the speed of 100 kilometers per hour, and when we do numerical problems in physics, we often use the unit of meters per second instead of kilometers per second. So we need to convert this into meters per second. Okay, so convert kilometer to meter. 1 kilometer is 1,000 meters. So in order to convert from kilometer to meters, you need to multiply this by 1,000. So let me just do that directly here. So 100 times 1,000 meters over, we have hour. 1 hour is 60 minutes, and we want seconds. So 1 minute is 60 seconds. So 60 times 60 seconds. So that's 60 times 60 seconds. So now we have our unit in meters per second. So if you do the calculation, that will give you 27.77 meters per second. And when you apply the brakes, you eventually stop the car. So final velocity would be 0. So when you hit the brakes, you will move forward, okay? And let's say the distance between your head and the steering wheel is, I don't know how big, how long is that distance? We can, here I estimated that as 1 meter, but it may be less than 1 meter, maybe half meter. You can use half meter if you want, but I used 1 meter distance between the steering wheel and the head, okay? So just before hitting the steering wheel, your head will travel 1 meter. Okay? So within that time, the airbag must deploy. Okay? Otherwise, you will hit the steering wheel. So we need to find this time that it takes to cover that distance. And the airbag should be deployed in the less time than this time. Okay, so let's find that time, and then we will say that it needs to be less than that time to protect the driver. So we have delta x is 1 meter. So again, we have 3 formulas. A is equal to V final minus V initial over T. Delta x is equal to V final squared minus V initial squared over 2 A. And delta x is equal to VIT plus 1/2 AT squared. So this we cannot use this one because there is no acceleration. This also we cannot use because there is no acceleration. So we are finding time. Okay, we're finding time. We have this one. We have initial velocity, and we need acceleration. Okay, so that means we can use this one also. So in that case, we first need to think about how to find the acceleration, because this one, both need acceleration. So let's first find acceleration, and then we can use that in this equation. So see, if we use this equation, then we have everything except acceleration. But we don't have time. Okay, so this one has 2 unknowns. We cannot have 2 unknowns. This is unknown. This is unknown. This is still not useful. How about this one? We know this one. Okay, this one is known. That's known. That's known. That's unknown. Okay, that means we can use this equation to find A, and once we know A, we can use either this one or this one to find the time. Okay, so let's use this one first to find time, to find acceleration. So delta x is equal to V final squared minus V initial squared over 2A, and I can do the cross multiplication. take this a up here and then delta x down here. Or if you want to do the math, you can do the algebra, you can do like this. So multiply both sides by 2a and divide both sides by delta x. Okay. So you can cancel that and that, cancel that and that. We don't need 2 here. Okay, let's not use 2, okay, because we don't want to keep the 2 here. So that means we have a here. A is equal to v final squared minus v initial squared over 2. This 2 is not cancelled, only a. 2 delta x. Okay, I'm just rearranging the terms. Okay, you can do that because it's a simple algebra. So let's plug in the numbers on that formula. V final, because the car will be at rest eventually, and then the initial one is what was the number we got from conversion? Is what was it? 27? 27.77. Okay, that's the initial speed. We have square. Don't forget that square, otherwise you won't get the right answer. And 2 delta x is how long will it travel before it hits, your head hits the steering wheel. So you can change this number. Okay, this is just estimation. I'm using 1 meter for the simplification purpose, but you can use 0.5 meters. It may not be exactly 1 meter. So this comes from estimation. Estimated distance between head and steering wheel. So if you do the calculation, that will give you negative, okay, minus 385.59 meters per second squared. Now we can use either this one or this one to find the time. So it will be simpler to just use the first one. So A is equal to V final minus V initial over T. Okay, you can rearrange the terms in terms of T. So T would be equal to V final minus V initial over A. Plug in the numbers. V final is 0. V initial is 27.77 meters per second. And acceleration, we just found it, negative 385.59 meters per second squared. And the calculation will give you 0.07 seconds. And then you also need to see the sig fig. So we have only one sig fig in the question. And this is the number with only one sig fig, because these are not significant. Only the non-zero one is significant. Okay, so that's the correct answer. Okay, so that's the worksheet. Please complete that and then submit on Gradescope. Now we'll look at the new worksheet, worksheet 2. Okay. So those who are on Zoom, you guys can download worksheet 2 from Blackboard. There is worksheet 2 on week 2 folder. So let's look at the first question. Let's see, let me first download this on the computer. So on the graph, you are given position versus time graph, and you are asked to find or x to determine the velocity versus time graph. So which one would be the right answer? Is it A or B or C, D? No, yeah, there's D. So, what can you tell about that flat part of the curve? What is that referring physically? What? Yeah, so the position is not changing, right, with time. It's just constant. The player is not moving up to some certain time. And then what's that slope, the slanted curve? What does that mean? We don't know about deceleration here. So think about when you have a position graph, think about velocity first, and then we can think about acceleration. First, think about velocity, okay? Because what the question is asking is about velocity. So what can you say about the velocity from that slanted graph, slanted line? So whenever you see a graph like this one has positive slope, okay? When you have a graph like this, it has negative slope, okay? And this has constant slope, okay? Like we did in the lab yesterday or on Wednesday. If you have a straight curve, straight best fit line, that means the velocity is constant, okay? It's moving at constant velocity. Here also, it's moving at constant velocity or constant slope. But if it is slanted up, the slope is positive, the velocity is positive. If it is slanted down, the velocity is negative. So the first part is not moving, okay? It's just velocity would be 0. So not moving means there's no velocity. And then second part, it's slanted down. That means there is velocity, but the velocity is negative, okay? So at this time, there is some velocity, which is constant velocity. It's down. Down means negative. If it is positive, it would be up here, but it's negative. So what's the right answer? Is it A? No? Which one is the right answer then? C, yes, I already gave the answer. So C. Again, the first part is 0 velocity, not moving. Second part, because it's slanted down, so velocity would be negative. Okay, so number 2, you are given velocity versus time graph. So you need to find the position versus time graph from that. So which one is the velocity versus position versus time graph? So you see this part, this is velocity. So that means it has positive velocity. And just from the previous question, what you know about the position versus time graph to get the positive velocity? whenever you have a velocity, that means position versus time graph would be slanted. Okay. Should it be slanted up or down? Just from our previous question. Up, yeah, so this one. So that will be for this part. And now we also have this part, okay? What that part means is zero velocity. Zero velocity means now it's not moving. Not moving means the position will remain same, okay? I'm just standing here and the time is passing, so the position doesn't change. Okay? So that's the position at that time, and that position will just keep constant. So you can decide which one is the right one. Okay, I will not tell you the right answer. Now with that, you should be able to figure that out. So let's look at number 3. So the figure on the right is position versus time graph of an object. What's the object's velocity at t is equal to 1.5 seconds? This is exactly the same kind of question as the lab question. So how did you find the velocity from position versus time graph in your lab? You guys remember? For a constant motion, you got this kind of graph. And how did you find the velocity from that? Yeah, you found the slope, right? You found delta x over delta t, rise over run. Now, the time at which you want to find the velocity is, so that's 1, that's 2, it's between 1 and 2, so here. And we know that from 1 to 2, the velocity is constant, okay? The slope, you see it's linear. If it is linear, the velocity here is constant. That means you can find the velocity anywhere in between 1 and 2, because no matter where you find, it will be same. So you can just draw a rise over run. The size of the rise and run doesn't matter. You can just draw this triangle. Oops. Now how to go back. I don't know what happened. Okay, it's now very blurred for some reason. Okay, let's just do it again. So I will let you guys figure that out, okay, while I'm doing this. So why don't you guys find the slope of the line from 1 to 2 seconds, and then I will see if your answer is correct or not. So what did you find? So we want to find delta x over delta t. If you consider the whole triangle, what's the delta x? What's that? Sorry? 20 meters. Yes, 20 meters. 20 meters. And for that 20 meter, your delta t would be 1 second, right? Because 2 minus 1 is 1. So that means velocity is 20 meters per second. Okay, let's look at number 4. A train is moving due west at a constant speed. So train moving due west at constant speed. A passenger notes that it takes 10 minutes to travel 12 kilometers. Okay. So to travel 12 kilometers, it takes 10 minutes. How long will it take to take the train to travel 60 kilometers? So this is constant speed motion, and when you are dealing with constant speed motion, you only have one equation. Okay, so for constant speed, because there is no acceleration, so you only have this equation: v is equal to delta x over delta t. So you can find v first. So v would be 12 kilometers. Just write km. 12 kilometers. Time to cover that distance is 10 minutes. That's the velocity. 1.2 kilometer per minute. Okay. And then now for this one, the velocity is still same because it's a constant velocity, but we need to find the time to cover 60 kilometers. So velocity is 1.2 kilometers per minute. Okay. Is equal to delta x is 60 kilometers and delta t. Okay. So you need to do the rearranging here. So delta t would be equal to 60 over 1.2 kilometers per minute. So if you do the math, what you get, is it 50? 50 minutes. Okay, you can do the calculation. I may be wrong. I'm just doing the math in my head, so it may be wrong. Is that 50 or? Okay. So let's look at last one. Okay, so number 5. We are almost out of time, so this will be the last one, and then we'll continue this next time. So we have velocity versus time graph, and it's asking what would be the position of the object at 4-second time. So look at the first part of the graph. This part. Okay, let's look at this part. So here, this object is traveling at 4 meters per second, and it travels at that speed for 2 minutes or 2 seconds. Okay, so that means the distance traveled within that time would be, this is a constant motion, so distance would be, velocity is distance over time for constant motion. So velocity times time. So velocity is 4 meters per second. Time is 2 seconds. Okay, so 8 meters. So it will travel 8 meters from here to here, which is also area under this curve. Okay, if you find the area under this curve, it would be 4 meters per second, length times width. Okay, length is 4, width is 2 seconds. That's 8. So whenever you find displacement from velocity versus time graph, okay, you find the area under the curve. Okay, displacement from VT graph, find area under the curve. So you can just find the area under this whole curve, like this is one part, and the other part is find the area of that triangle. So area of triangle is 1/2 base. Base is 2 seconds, and height is 4 seconds, 4 meters per second. So that gives us 4 meters per second. So the total distance traveled within that time, 4-second time, would be 12 meters. Actually, this is meters. Okay, and the position of the object would be 12 meters from its initial point. Okay, so I think I will stop at this point because we are out of time. We'll continue this in the next lecture.